Continuing the conversation with Pascal's triangle, we're going to investigate one interesting property that it has, and there's so many. But if we look down the middle, so let me draw a line right down the middle of Pascal's triangle. And what do you notice? We notice that the numbers increase. Whoa, that's not how an increase works. Increase as we go toward the middle, and here they're equal, and now they're going to decrease. The same thing here, they're going to increase as we get toward the middle and then decrease. They increase and then they decrease. So that's a property that's called unimodality. So the theorem that we want to prove is that the binomial coefficients have this. Theorem, the binomial coefficients are unimodal. Unimodal, again, means that they go up and then they go down. Let me write down more explicitly what I mean by this. I mean that n choose k is less than or equal to n choose k plus 1 up until the halfway point. So if k is less than or equal to n minus 1 over 2, and the opposite inequality holds on the other side. If k is greater than or equal to n minus 1 over 2. So this is the statement that we want to prove. And the way we're going to do it is going to be fairly boring and algebraic, but I think it's an important idea for how to handle one of these algebraic proofs. Okay, so this would be an example to go back to when you're trying to work out some of these technical analytic properties that are maybe a little challenging at times. So I'm going to make an assumption. I'm going to pick a case. We technically need to do both, but for the interest of brevity, I'll just do one. I'll choose k less than or equal to n minus 1 over 2. Okay, that's what we're going to get to assume. Now, what do I want to show? I want to show the top inequality, which I'll write down again just because it never hurts to remind yourself what you're trying to prove. This is what I want to show. I want to show that n choose k is less than or equal to n choose k plus 1. Now, we could start with this inequality and kind of go down, put a question mark above it, but that really drives most mathematicians, present company included, insane. So instead, let's just write down what both sides are and do them in parallel. And when we can finally conclude something about an inequality, we can state it and make sure that we kept it. Because we're doing an inequality and not an equality, here, we need to be really careful that we never flip this inequality, right? We're going to flip that whenever we multiply by a negative number. So make sure whatever we're doing is very positive. Okay, so on the one side, I'm going to have n choose k, and counter to that, I'm going to have n choose k plus 1. The first step is to expand, because these are weird symbols that don't really have much analytic value until we write down their expressions. So this is n factorial divided by k factorial n minus k factorial. Over here, we have n factorial divided by k plus 1 factorial n minus k minus 1 factorial. Now, keep in mind that until we use this fact, we should not be able to conclude which of these is bigger, because it depends very heavily on this fact. Okay? So don't jump the gun and don't draw conclusions until we really see how to use it. The first thing we want to do is get rid of the ridiculous denominators. Denominators are awful. We can cross multiply. That'll be multiplying by positive numbers on both sides, so that's completely allowed. So I'm going to do that. I'm going to cross multiply to get rid of my denominators. If there's an inequality, that will not reverse it. I do want to check that, and it is the case here. So I've just multiplied through on that denominator, and over here, I'll get k factorial n minus k factorial n factorial. Now I'm going to divide, never divide by 0, of course, but also don't divide by a negative number for the same reason. We don't want to flip our inequality. But there are lots of things that we can divide by. Maybe we'll pay careful attention to them. So here's this n factorial and this n factorial. We can totally cancel those guys out. Here we have a k plus 1 factorial. I can cancel out the factorial part with this whole k factorial here, right? Because k plus 1 factorial is k plus 1 times k factorial. This is the fact that I'm going to end up using a lot. It's worth writing it down just so that you remember. This is k plus 1 times k factorial. Okay, and then a similar thing is going to happen with the term here, this now is the smaller term. So I'm going to knock this whole thing out, and I'm going to take out this guy's factorial. So what am I going to be left with? On the left, I'm left with k plus 1. And on the right, I'm left with n minus k. So which is bigger, k plus 1 or n minus k? It depends. But I have this thing I get to assume that's going to help me make a deduction. Now, if I wanted to, I could start plugging in here, but I want to be really careful not to screw this up. So what I see here is k compared to stuff that has to do with n. So what I want to do is on one side, I want to isolate the k. So that's my goal. I'm going to move the k across. I'll get 2k. I might as well kick the 1 to the other side, and I get n minus 1. One more step, dividing by 2. 2 is a positive number, so I'm happy to divide by it without changing my inequality, and I get this. Now, I'm going to use what I supposed, which is, this is by the assumption that k is less than or equal to n minus 1 over 2. That is literally what we concluded. Excuse me. So we can carry our inequality up the chain, and we can conclude that the theorem is indeed true. You can carry out literally the exact same analysis. If we flip this inequality that we're assuming here, it will flip this, and then we'll make the other assumption, which is what this statement is. So definitely the relationship between these two is the same as the relationship between these two. And in fact, if you didn't know this theorem and you wanted to prove something about it and you weren't sure what this cutoff was, by doing this manipulation, you could deduce what it is. So that's a handy skill if you want to go more on the analytic side for doing some numerical analysis of interesting sequences that we come across.